let's investigate difference quotients. So the difference quotient is used to calculate the slope of a secant line between 2 points of a function. So what does that mean? Let's say we're given some x and y axis, right? And we have this line. Now, we want to calculate, well, how can I find this straight line that passes through 2 points on this unknown function? Well, we can sort of think about it as the first point given is x sub 0. So that would be the first point, the first x point. Now I can also assign a y point, which would be f of x sub 0. Okay, so this is a little bit of an investigation. So it might be difficult to follow at first, but it should make sense a bit later. So if we walk all the way and create this rise over run, right? This rise over run. Well, we know that a rise over run referred to a gradient or a slope. Okay, slope. So now we've seen that, well, we're sort of on the path of calculating some sort of slope, right? So I can assign, we know, well, in high school, you learned that y2 minus y1 over x2 minus x1. This is given a mathematical notation of m. Well, I can also assign this as delta x over delta y. But I can also say, well, this is known as delta f, since it's the change in my height, because I'm working with the f of x, right? So let's see. So how do I get this new point? Well, this new point, I can say, well, it's going to be this coordinate plus my change, right? So it's x sub 0 plus delta x. And now if I want to find my new height, well, I can say, well, this is going to be f of x sub 0 plus delta x, 2. So how can we write that mathematically now? Well, mathematically, we can write it like this. Well, it's going to be my change in y over the change in x, but instead of using y and x, now I'm going to use the coordinates I have in this case. So this would be my second y coordinate, my first y coordinate, and this one would be my first x coordinate and my second x coordinate. So I can rewrite this as, well, I have the f of x sub 0 plus delta x minus the f of x, and I can place this over the change in x. And the change in x in this case is simply going to be delta x. Now what if I want to rewrite this? Well, before I'm going to continue, we can see, well, the limit as this function approaches 0, I can then see what happens to the slope the closer I get to 0. So now all of a sudden we can add some limits. Well, we can say the limit as x sub 0 approaches 0 is going to give me my slope, and I can see what happens when I get closer to 0. Okay, well, all of this looks a little bit complicated. So what about we simplify this? What about we change delta x, we change this to h? So what does it look like now? Well, now all of a sudden I can say, well, the f of x plus h, well, we're going to change our delta x to h now, okay? Minus the f of x over h. And instead of using the limit of x sub 0 approaches 0, we're going to have the limit as h approaches 0. So we have it in a little bit of a simplified form, and this is the form you are probably taught in high school. So this is how the form was derived. So we're trying to find some slope between 2 points, which is then known as a secant line. Okay. Well, let's see. Well, it tells us that the derivative would be then the limit as h approaches 0 to this thing I just created. Well, let's see if this is true, right? So let's say I'm given the f of x is equal to x squared. Now I want to find f prime of x. Well, if we use the power method, we know we're just going to simply multiply this one forward and subtract 1. So then my derivative of the f of x, where x is x squared, is simply going to be 2x. But let's say we had to prove this with different quotients now. So I can then say, well, the limit as h approaches 0, because I want to see what happens at this 0 mark, the closer I get to 0. Actually, the closer the change gets to 0. So I can then rewrite, since the f of x is given to us as x squared, and the f of x plus h would therefore then be x plus h squared. So I can rewrite this. I can say, well, the f of x, excuse me, it's going to be x plus h squared minus x squared over h as the limit approaches 0. Now, if all of this I was talking about is true, well, then this method should give me the derivative of the line, right? It should give me some derivative that should be equal to this 2x. Well, first things first, we always need to simplify these type of equations when we work with limits, okay? So the limit as h approaches 0, I'm going to expand this, which is then going to be x squared plus 2xh plus h squared minus x squared over h. Now you might be wondering, well, where did this come from? Well, this came from for expanding these two brackets using the FOIL method. So x times x is x squared, x times h is plus xh, h times x is plus xh, and then we have plus h squared. So I can then add the like terms, which is then going to give me 2xh plus h squared. Okay, now we can simplify. Well, I'm going to delete these two. Why is that? And you'll notice every time you do these difference in quotient or different quotient equations, you'll see that the first term and the final term always cancels each other out. You'll see a common trend when working with single variables. Okay, so in this case we have x squared minus x squared is obviously 0. So then I can now rewrite, well, the limit as h approaches 0. I'm going to factor now. I'm going to factor with an h, and we have h x2 plus h over h. Now I can simplify. H can simplify with h, and after it's in its simplest form, now I will direct substitute my 0. So therefore I would have x2 plus h, or plus 0, and in this case we have 2x. So there I just found the derivative of the line by using different quotients. Okay, so let's do another one. Let's see the limit as h approaches 0, and the function given is e raised to the x. Now we know the derivative of e raised to the x is e raised to the x, but how do we conclude this? How do we know that this is actually the derivative instead of just being told, hey, derivative of e to the x is e to the x? Well, let's do the same thing. So the f of x is given to ex. So therefore the f of x plus h should be then ex plus h. So let's do it. Minus e to the x over h. Now I can expand. I can expand my e's. So e to the x times e to the h minus e to the x over h. Therefore, I can factor now, because both of my expressions contain e to the x. Look, e to the x and e to the x. I can factor. So I can then say, well, e raised to the x is going to be e to the h minus 1 over h. Now, considering this is a constant, I can move this forward to in front of the limit. Now, why is that? Since the limit as h approaches 0 is going to give me this value, I can therefore then just multiply this value with my e to the x. So it really doesn't actually matter. So I can simply move this forward because it's a constant term, right? So e to the x, the limit times the limit as h approaches 0 is going to be e to the h minus 1 over h. Now, if we put in 0, let's see what happens if I put in 0. Well, if I put 0, I have e to the 0 minus 1 over 0. This is going to give me 1 minus 1 over 0, which is 0 over 0. Now, even L'Hopital doesn't work in this situation, because we just get, again, 0 over 0. So, what does this mean? Does this mean e to the x times undefined? Well, that makes no sense, right? Because we know our final answer should be e to the x. So how do we get that? Well, we can use a value 0.001. 0.001 is very close to 0. Very, very close. So we can use that. And then we can see what happens. Now we can see the closer values we put in e to the, or in h, instead of h, we put 0.001, 0.001. In that case, we can see, well, the limit as h approaches 0 for e to the h minus 1 over h suggests that the limit is 1. It doesn't necessarily tell us 1 because we cannot exactly find 1. But we can make the assumption that the limit is going to be 1. Okay? I recommend you test this on a calculator. Just keep putting in values all the way closer to 0, but don't use 0, because if you use 0, you'll find undefined. And we can therefore make this concrete conclusion that, I mean, not really, to be honest, but we'll find 1. So therefore, we can then say, well, if the limit as h approaches 0 under the assumption is 1, we can say, well, e to the x times 1, and therefore we get e to the x. I would highly recommend you go use a calculator and try this one. It's a very interesting derivative, this e value. Okay, so now I'm going to do one more. What about this one? The limit as h approaches 0 for a to the x. So let's say we're given the function a to the x. Well, the derivative of a to the x is a to the x times ln a. But how do we find that? Well, let's use our different quotients. Okay, try solve this one. So we can therefore have a to the x plus h minus a to the x over h. Now we're going to do the exact same thing we did a little bit earlier, where we split these two up. Again, then we factor. So I can then say a to the x times a to the h minus a to the x over h. We can now factorize. So the limit as h approaches 0. So the only time you stop writing the limit as h approaches 0 is when you're in your final factored form and you want to substitute the 0 now. Then you can stop writing the limit as h approaches 0, okay? So therefore we have a to the x times a to the h minus 1 over h. So I can therefore say, well, a to the x times the limit as a approaches 0 of a to the h minus 1 over h. And the limit in this case, as we're approaching 0, is actually going to be the natural log of whatever is given. Okay, I'll do a further investigation on this, but for now let's just look at the theory behind it. So therefore we can then say, well, a to the x is going to be times the limit or the natural log of a, where the limit of h approaches 0 to a to the h minus 1 over h. And then we get our derivative. Now you might wonder, well, what if it becomes a bit longer and more complicated? Well, let me do one more actually. Let's do this one. Let's say the function is given, the f of x is equal to 2x cubed. Well, if I simply derive this with the power rule, okay, the power rule tells me that you're going to take nx n minus 1, which means you're going to multiply whatever's forward and you're going to subtract 1. So we can quickly conclude that f prime of x, oh, by the way, this is from, this is Isaac Newton's prime notation. Okay, Isaac Newton's prime notation. He loved using prime. So we have 6x squared. But let's go see if this is true. Well, now we know the limit as h approaches 0 is therefore going to be 2 times x plus h cubed minus 2x3 over h. So the limit as h approaches 0 is simply going to be, well, I'm going to expand this the easy way. Okay, so let's expand it the easy way. This is the method that might be easier to most students. So earlier we said, well, it's going to be, if I expand this, it looks something like this. I'm going to do it one by one. We've already calculated this one. X plus h times x plus h is going to give me 2xh plus h squared. Now I'm going to multiply this with the coefficient of x plus h. So that gives me x to the 3. That gives me 2x squared h, and that gives me plus h, or that gives me xh squared. Okay, so this one's done. I just multiplied that with this, this, and this. Now I'm going to multiply my h with this, this, and this. And then we're going to add the like terms. So h times x squared is going to give me, I'm going to place it over here to make it a bit easier. Ideally, you want to place all of the remaining values over here, but for the video purpose, I'm going to place it below so we don't get confused. Okay, so this is going to give me x squared h. Then I have h plus 2xh. So in that case, it's going to give me plus 2xh squared. And then we have h3, or h plus h, and that gives me plus h to the 3. So now I can add the like terms over here. So this gives me x cubed plus 3x squared h plus 3x h squared plus h cubed. And now, before I write it in here, I still need to multiply all of this with a 2, because there's a 2 in front of my parentheses. Okay, so I'm going to multiply it in this is called the distributive property. Okay, so that then gives me 2x cubed plus 6x squared h plus 3xh cubed plus h cubed minus 2x3 cubed, and then we have over h. Okay, now we're left with this bad boy. So let's see. Well, we know the first and the last term will always cancel each other out if my equation is correct. So now I have the limit as h approaches 0. And we're going to factor, okay? We're going to factor with an h, because look, it contains an h, contains an h, contains an h. So let's factor. So now we have h is going to be 6x squared plus 3x. I remove one of the h's, plus h squared over h. I'm going to substitute or subtract. And now I'm going to direct substitute. So it's going to be 6x squared plus 3x times 0 plus 0 squared. And if I do this, well, I get 6x squared, since that's 0 and this is 0. And look at that. We found my gradient of the secant line. Okay, so this was a little bit of an investigation where we spoke about difference in quotients. Sometimes you might have to sometimes you might have to prove it in exams. Most of the times this is completely ignored, but to understand the beauty behind calculus, it's worth learning all the theory. If you deciding of going into a field of, let's say, like economics, computer science, web development, etc., etc., you might mainly need calculus for all those subjects, or you might have to take some calculus course. Anyway, have a good one.